Alkyl halides. Introduction. The compounds obtained by the replacement of one or more hydrogen atoms of a hydrocarbon by a corresponding number of halogen atoms are known as halogen derivatives. These derivatives are subdivided as mono, di, tri, tetra halogen derivatives according to the number of halogen atoms present in the molecule. In addition, the halogen derivatives may be further classified into different classes depending upon the nature of parent hydrocarbon. There are two main classes which may be further subdivided as given below. Aliphatic halogen derivatives. These are halogen derivatives of aliphatic hydrocarbon in which one or more hydrogen atoms of the hydrocarbon have been replaced by an equal number of halogen atoms. Depending upon the nature of aliphatic hydrocarbon, they are further divided into three types. Haloalkanes. The halogen derivatives such as CH3Cl, CH2Cl2 and CHCl3 obtained by the replacement of one or more hydrogen atoms of alkanes are known as halogen derivatives of alkanes. These compounds are very reactive and undergo numerous reactions which are used in the preparation of large number of aliphatic compounds. Monohalogen derivatives of alkanes are commonly known as alkyl halides as discussed below. Haloalkanes. These are halogen derivatives of alkenes. Monohalogen derivatives of alkenes are known as alkyl halides. For example, vinyl chloride, allyl chloride. Haloalkynes. These are halogen derivatives of alkynes. Monohalogen derivatives of alkynes are called alkyl halides. For example, chloroethane, 3-chloropropene. Halogen derivatives of aromatic hydrocarbon. These are halogen derivatives obtained by the replacement of one or more hydrogen atoms of aromatic hydrocarbons by halogen atoms. These may be subdivided as nuclear substituted derivatives. These are halogen derivatives of aromatic hydrocarbon in which the halogen atom is directly attached to the benzene nucleus. For example, chlorobenzene, orthobromotoluene. Side chain substituted derivatives. These are halogen derivatives of aromatic hydrocarbon in which the halogen is linked to the carbon of side chain. For example, benzyl chloride, benzyl dichloride. The side chain derivatives are very reactive compounds which are similar to halogen derivatives of alkanes. On the other hand, nuclear derivatives are much less reactive and undergo only a few substitution reactions under strong condition. In this chapter, we shall discuss about the chemistry of alkyl halides. Alkyl halides. Alkyl halides or monohalogen derivatives of alkanes are the compounds obtained by the replacement of one hydrogen atom of an alkane by a halogen atom. They have the general formula CnH2n plus 1x or Rx, where X represents a halogen atom and CnH2n plus 1 or R stands for an alkyl group. For example, methyl chloride, ethyl bromide, isopropyl iodide. In a wider sense, however, alkyl halide include even side chain monohalogen derivatives of alkyl benzenes and cycloalkanes. For example, benzyl chloride, cyclohexyl chloride. It must be noted, however, that the compounds containing a halogen directly attached to a benzene ring are in no case covered by the term alkyl halide. Such compounds are called aryl halides, differ widely from alkyl halides in their method of preparation and properties and are treated separately. Classification of alkyl halides. Alkyl halides may be further subdivided as primary, secondary and tertiary halides according as the halogen is attached to primary, secondary or tertiary carbon atom. For example, primary halides N-bromyl iodide, isobutyl bromide. Example of secondary halides isopropyl chloride, secondary butyl bromide. Example of tertiary halides tert butyl bromide, tert pentyl iodide. Alkyl halides are among the most reactive organic compound as the alkyl halogens can be easily replaced by nucleophilic reagents. Substituted alkyl halide exhibit the properties of other substituent groups also. For example, benzyl chloride displays the reaction of aromatic nucleus also in addition to the characteristic reaction of alkyl halides. It may be noted that fluoroderivatives of alkanes, also known as fluorocarbon, differ from other halogen derivatives in many respects. For this reason, alkyl fluoride and other fluorocarbon are treated separately from chloro, bromo and iodo derivatives. As such, we shall confine our discussion to alkyl chlorides, bromides and iodides only which are quite similar to each other. Nomenclature. Common system. In this system, individual alkyl halides are named as halides of the particular alkyl group present in the molecule. For example, CH3Cl is named methyl chloride while CH3CH2I is named ethyl iodide and so on. IPSC system. According to this system, these compounds are named as given below. First, the longest state chain of carbon atoms including the carbon which carries the halogen is selected and the alkane corresponding to this chain is taken as the parent alkane. The state chain is numbered from the end, which gives the smallest number to the carbon carrying the halogen. The names of the halogen and the side chain along with their points of attachment are added before the name of the parent alkane. For example, 2-chloro 3,4-dimethyl pentane. Structural isomerism in alkyl halides. Higher members of alkyl halides show two types of structural isomerism as given below. Chain isomerism. Alkyl halides containing 4 or more carbon atoms can exhibit chain isomerism. For example, the two chain isomers of C4H9Cl are as follow: 1-chlorobutane or 1-chloro-2-methylpropane. Position isomerism. Alkyl halides having 3 or more carbon atoms can exist as position isomers. For example, C3H7I can exist in the form of two position isomers as shown below: 1-idopropane, 2-idopropane. In general, the total number of structural isomers of an alkyl halide is 2n-2, where n is the number of carbon atoms. Thus, there are 4 isomers having the molecular formula C4H9Cl and 8 isomers having the molecular formula C5H. Methods of preparation. The important methods of preparation of haloalkanes are discussed below. First, from alcohols. Haloalkanes are generally prepared by the replacement of hydroxy group of an alcohol by a halogen atom. This can be done by using different halogenating reagents as given below. First, action of hydrogen halides. Alcohols are converted into haloalkanes by reaction with hydrogen halides under stable condition. ROH plus HX gives rise Rx plus H2O. Primary and secondary alkyl halides are obtained by passing HCl gas into corresponding alcohol in the presence of N-hydrazine chloride. This is also known as Grove's process. For example, CH3, CH2OH plus HCl gas in presence of N-hydrazine and ZnCl2 gives CH3CH2Cl plus H2O. Tertiary alkyl chlorides can however be obtained by reaction between tertiary alcohol and concentrated HCl even in the absence of anhydrous ZnCl2. For example, 2-methyl-2-propanol concentrated plus concentrated HCl gives rise to chloro-2-methylpropane. Alkyl bromides and iodides can be obtained by heating the alcohol with excess of constant boiling HBr or HI. For example, CH3CH2CH2OH plus HBr gives rise CH3CH2CH2Br plus H2O, or ethanol plus HI gives iodoethane plus H2O. But in actual practice, hydrogen bromide and iodide are usually prepared in situ by using sodium bromide and concentrated sulfuric acid or potassium iodide and phosphoric acid. For example, CH3CH2OH plus NaBr plus H2SO4 gives rise bromoethane plus H2O plus NaHSO4. CH3OH plus Ki plus H3PO4 gives rise CH3I plus H2O plus KH2PO4. Action of phosphorus halides. Action of phosphorus halides on alcohols converted them readily into alkyl halides. 3ROH plus PX3 gives rise 3RX plus H3PO3. Thus, alkyl chlorides are produced by reaction between alcohols and PCl3 or PCl5. For example, CH3CH2CH2OH plus PCl5 gives rise CH3CH2CH2Cl plus POCl3 plus HCl, or 2-propanol gives rise to chloropropane plus H3PO3. In case of preparation of alkyl bromides and iodides, PBr3 and PI3 required for the reaction are not very stable compounds. These are generally produced in situ by the action of red phosphorus on bromine or iodine. That is, 2p plus 3i2 gives rise to pi3, or 1 propanol gives rise 1 iodopropane, or 2p plus 3br to 2pbr gives rise 2pbr3, or ethanol gives rise bromoethane. Action of thionyl chloride. Alkyl chlorides are conventionally obtained by reaction between thionyl chloride and alcohols in the presence of pyridine. ROH plus thionyl chloride in presence of pyridine gives rise RCl plus SO2 plus HCl. For example, ethanol plus SOCl2 in presence of pyridine gives rise chloroethane plus SO2 plus HCl. Addition of hydrogen halides to alkenes. Addition of hydrogen halides to alkenes yields alkyl halides. For example, CH2 double bond CH2 plus IHI gives rise CH3CH2I. CH3CH double bond CH2 plus HCl gives rise CH3CHCl CH3. It may be recalled that in case of unsymmetrical alkenes, the above addition reaction takes place according to Markovni's rule. The rule states that when addition across an unsymmetrical double bond takes place, the positive part of the addendum goes to the carbon atom with the greater number of hydrogen atoms. It should be remembered, however, that Markovni's rule is not always applicable. In the presence of organic peroxide, the addition of HBr to alkenes does not follow the said rule. This anti-Markovni's addition to alkenes is known as peroxide effect or Kharas effect. Example, propene plus HBr in the absence of peroxide gives 2 bromopropane, or in the presence of peroxide gives 1 bromopropane. Third method of preparation. Halogenation of alkanes. Direct halogenation of alkanes under the influence of light result in the formation of alkyl halide. Methane plus Cl2 in presence of Hb gives rise CH3Cl plus HCl. In actual practice, this method result in the formation of mixture of mono, di, tri and tetra halogenated compounds. At the same time, even monohalogen of higher alkanes gives a mixture of isomeric monosubstituted products. For example, CH3CH2CH3 in presence of Cl2 or Hb gives rise CH3CH2 CH2Cl plus CH3CHCl CH3 or minus HCl. Therefore, this method is used only industrial where complete separation of the mixture obtained may not be necessary. Iodo and fluoro derivatives are seldom prepared by this method. This is because iodination is reversible in nature while fluorination takes place explosively. Fourth, bihalide exchange or Finkelstein reaction. Alkyl iodides can be conventionally prepared by treating the corresponding alkyl bromide or chloride with a solution of sodium iodide in acetone. For example, bromoethane plus NaI in presence of acetone gives rise iodoethane plus NaBr. As compared to sodium iodide, sodium bromide is less soluble in acetone and gets separated during the course of the reaction. As a result, the reaction equilibrium shifts in the forward direction. Fifth, from silver salts of carboxylic acid, alkyl chlorides and bromides can be prepared by the action of chlorine or bromine on the silver salts of certain carboxylic acid dissolved in carbon tetrachloride. For example, RCOOAg plus Br2 in presence of CCl4 gives rise RBr plus CO2 plus AgBr. While alkyl bromides can be obtained in fairly good yields by this method, the yields of alkyl chlorides are poor. With iodine, silver salts give ester instead of alkyl iodides. RCOOAg plus I2 in presence of CCl4 gives rise RCOOR plus CO2 plus 2AgI. Physical properties. Physical state. The lower alkyl halides such as methyl chloride, methyl bromide and ethyl chloride are colorless gases. Methyl iodide and majority of higher members are colorless, pleasant smelling liquids. Members with very high molecular weights are solid. Alkyl iodides turn brown on standing due to their decomposition by light. Boiling points. In general, alkyl halides have considerably higher boiling points than the corresponding hydrocarbons. This is due to the fact that alkyl halides have higher molecular masses than corresponding alkanes and are also polar in nature. Therefore, they have stronger intermolecular forces of attraction than the corresponding alkanes. Amongst the alkyl halides themselves, the following points may be noted. First, for a given alkyl group, the boiling points of haloalkanes follow the order Ri, Rb, or Rcl. This is because the magnitude of intermolecular forces decreases with the decrease in the size of halogen atom. For a given halogen, the boiling point of alkyl halide increases with increase in the size of alkyl group. This can be attributed to the increase in molecular size, which leads to greater intermolecular interaction. Third, for isomeric alkyl halides, the boiling point decreases with branching. This is because branching of the chain decreases the surface area and consequently the intermolecular forces of attraction become weaker. Solubility. Even though they are polar in nature, alkyl halides are insoluble in water. This is because alkyl halides can neither form hydrogen bonds with water nor break the hydrogen bonds already existing between water molecules. They are, however, soluble in the organic solvents. Density. Alkyl chlorides are lighter than water, whereas bromides and iodides are heavier, the density being in the order Ri, Rbr, Rbr, Rcl. With increasing size of the alkyl group, the density goes on decreasing. Chemical properties. Alkyl halides are one of the most reactive classes of organic compounds. They undergo a variety of synthetically important reactions involving nucleophilic substitution, elimination, reduction, and formation of Grignard reagents. Naturally, therefore, they are regarded as one of the most important synthetic reagents in organic chemistry. The important reaction of alkyl halides are discussed below. Nucleophilic substitution reaction, or also known as SN reaction. Alkyl halides contain sigma bond between sp3 hybridized carbon and a halogen atom. The halogen atom is more electronegative than the carbon atom attached to it. Therefore, the carbon-halogen bond is partially polarized, the carbon acquiring small positive charge and the halogen getting some negative charge. The positively polarized carbon can be easily attacked by nucleophilic reagents. When an alkyl halide is treated with a strong nucleophilic reagent, the halogen is readily displaced as a halide ion as shown below. Thus, alkyl halides undergo a number of reactions called nucleophilic substitution reaction, in which the halogen is displaced as halide ion by stronger nucleophilic reagents, giving a large variety of products. The nucleophilic reagent may be negatively charged ions such as OH negative, Cn negative, and OR, generally added in the form of its sodium or potassium salt, or a neutral molecule having an atom with a lone pair of electrons such as NH3 and RNH2. The halogen atom which departs along with the bonding pair of electrons is known as leaving group. It may be seen that in the nucleophilic substitution reaction, the carbon-halogen bond undergoes heterolytic cleavage and the lone pair of electrons of nucleophile is used to form a new bond with carbon atom. Order of reactivity with respect to halogen. The strength of carbon-halogen bond in different alkyl halides and therefore the reactivity of alkyl halides depend upon the nature of halogen atom. It is found that the carbon-halogen bond strength follows the order CF, CCl, CBr, Ci. The CF bond has the smallest bond length due to the small size of fluorine end. Therefore, it has the maximum strength. As the bond length goes on increasing with the increase in the size of the halogen atom, bond strength goes on decreasing. Since Ci bond is the least strong, it is broken most easily, so that the alkyl iodides are the most reactive and the reactivity decreases in the order Ri, Rbr, Rcl, Rf. In other words, it can be said that iodide ion departs from the alkyl halides most readily and is the best leaving group. The order of ease of elimination of leaving group is I negative, Br negative, Cl negative, F negative. Order of reactivity with respect to different alkyl groups. For different alkyl halides containing the same halogen, the order of reactivity is largely determined by the exact mechanism of the reaction as discussed subsequently. First, replacement of halogen by a hydroxyl group, formation of alcohols. When treated with aqueous solution of potassium hydroxide or sodium hydroxide or most silver oxide Ag2O or H2O, alkyl halides react with OH negative ions to form alcohols. For example, C2H5I plus K positive OH negative gives rise C2H5OH plus Ki. Replacement of halogen by alkoxyl group. Formation of ether. On treatment with sodium alkoxide, alkyl halides react with alkoxide ions to form ethers. This reaction is also called Williamson synthesis and is useful method of preparing ether. For example, ethyl bromide plus sodium ethoxide gives rise diethyl ether plus NaBr. Alkyl halides also react with dry silver oxide to form ethers. For example, 2C2H5Br plus Ag2O gives rise C2H5O C2H5 plus 2AgBr. Third, replacement of halogen by cyano group or formation of cyanide or nitriles. When treated with alcoholic solution of potassium cyanides, alkyl halide react with cyanide ions Cn negative to furnish mainly cyanides or nitriles along with a small amount of isocyanides. Rx plus Cn negative gives rise RC triple bond N plus X negative. For example, methyl iodide plus KCN gives rise methyl cyanide plus Ki. Hydrolysis of cyanides themselves yields amide or carboxylic acid depending upon reaction condition. Replacement of halogen by isocyanide group. Formation of isocyanides or isonitriles. Alkyl halides react with silver cyanide at high temperature to give isocyanides along with small quantities of cyanides. Rx plus AgCN gives rise isocyanide plus AgX. For example, CH3I plus AgCN gives rise CH3N triple bond C plus AgX. Explanation of simultaneous formation of cyanides and isocyanides. Cyanide ion is a typical nucleophilic reagent as it has got a lone pair of electron on carbon and another lone pair on nitrogen. Therefore, carbon as well as nitrogen can act as nucleophilic centers. Accordingly, either carbon or nitrogen may get linked to alkyl group to give rise to cyanides or isocyanides. A nucleophile such as cyanide ion which has more than one reactive site is known as ambident nucleophile. Alkali metal cyanides NaCN or KCN are predominantly ionic compounds and cyanide ion generated by them attacks alkyl halides preferably through its carbon atom. This is because the C bond formed when the attack takes place through carbon of C triple bond N is more stable than the CN bond which would be formed if the attack were to take place through nitrogen of C triple bond N. Has such reaction between NaCN or KCN and alkyl halide yield alkyl cyanide as the main product. On the other hand, AgCN is a predominantly covalent compound. As such, only the lone pair of electron on nitrogen is available for bond formation. Therefore, reaction between AgCN and alkyl halides yields alkyl isocyanides as the main product. Fifth, replacement of halogen by carboxylate group. Formation of esters. When heated with silver salt of a carboxylic acid, alkyl halides react with carboxylate ions RCO negative to yield esters. For example, ethyl iodide plus silver acetate gives rise ethyl acetate. Sixth, replacement of halogen by nitro group NO2 or formation of nitroalkanes. On heating with silver nitrite, alkyl halides give mainly nitroalkanes along with a small amount of alkyl nitrite. For example, C2H5 I plus AgNO2 gives rise nitroethane plus NaI. 7th, replacement of halogen by nitrite group. Formation of nitrites. On reaction of alkyl halides with sodium or potassium nitrite, however, the main product is alkyl nitrile. For example, methyl iodide plus NaNO2 gives rise methyl nitrite plus NaI. Explanation. Formation of nitroalkanes as well as nitrites in the above reaction is due to the fact that NO2 negative ion is also an ambient nucleophile. The two reactive sites in it are oxygen and nitrogen. Since AgNO2 is predominantly covalent compound on the lone pair of electron on nitrogen is available for nucleophilic attack on alkyl halides. This naturally leads to the formation of nitroalkanes as the main products. In case NaNO2 or KNO2, each of which is predominantly ionic compounds, is used in the reaction with alkyl halide, the NO2 negative ion attacks the alkyl carbon preferably through oxygen to form alkyl nitrile as the main products. 8th, replacement of halogen by amino group या formation of amines. On being heated with amine alcoholic solution of ammonia alkyl halides first change into primary amine as the amine formed is nucleophilic itself. It reacts further with alkyl halide to yield ultimately a mixture of primary, secondary and tertiary amine and quaternary ammonium salt. This reaction is known as Hofmann monolysis reaction. For example, C2H5I plus NH3 alcoholic gives rise ethyl amine plus HI. In actual practice, the alkyl halide is initially attacked by nucleophilic ammonia to form a primary amine salt. This salt further undergoes an equilibrium reaction with ammonia to give free primary amine. The free primary amine reacts further with alkyl halide as already explained. 9th, replacement of halogen by hydrosulfide group. Formation of thioalcohols. When treated with potassium hydrosulfide, alkyl halides react with hydrosulfide ion SH negative to form thioalcohols. For example, ethyl iodide plus Ka positive SH negative gives rise ethyl thioalcohol plus Ki. 10th, replacement of halogen by mercaptide group. Formation of thioethers. When treated with sodium mercaptide, alkyl halides react with mercaptide ion Rs negative and are converted into thioethers. For example, C2H5Br plus C2H5S negative Na positive gives rise diethyl thioether plus NaBr. 11th, replacement of halogen by alkyl group. Formation of alkanes or Bird's reaction. On reaction with sodium in dry ether, saturated alkyl halides change into alkanes. It is believed that sodium initially reacts with a molecule of alkyl halide to form an alkyl carbanion. This, being nucleophilic in character, reacts further with another molecule of alkyl halide to yield an alkene. For example, methyl bromide plus 2Na dry ether in presence of dry ether gives ethane plus 2NaBr. 12th, replacement of halogen by alkynyl group. Formation of alkynes. When treated with sodium salt of alkynes, alkyl halides react with alkynyl ion R C triple bond C to produce higher alkynes. For example, ethyl bromide plus sodium acetylide gives rise 1-butene plus NaBr. 13th, a replacement by groups derived from malonic ester or acetoacetic ester. Formation of substituted malonic esters and acetoacetic esters. On reaction with carbanions derived from malonic ester or acetoacetic esters, alkyl halides give rise to substituted malonic ester or substituted acetoacetic ester. For example, carbonine derived from malonic esters or alkyl derivative of malonic esters. 14th, replacement of halogen by aryl group. Formation of alkyl benzene. Friedel-Crafts reaction. On treatment with benzene and its homologous alkyl halide furnish alkyl benzenes. For example, CH3Cl plus C6HCX in presence of anhydrous AlCl3 gives rise to toluene plus HCl. Other reaction. 15th, elimination reaction. Dehydrohalogenation. When heated with a waste such as alcoholic solution of potassium hydroxide or sodiamide, and alkyl halide undergoes elimination reaction by the loss of halide ion together with hydrogen ion from an adjacent carbon. Example of beta hydrogen. Thus, alkyl halides get dehydrohalogenated on reaction with alcoholic potash or sodium to form alkenes. For example, N-propyl bromide gives rise propylene plus KBr plus H2O. Sometimes an alkyl halide can undergo elimination in two different ways, forming a mixture of products. The preferred product in such a reaction is the alkene, which is more highly branched at the doubly bounded carbon atoms. This generalization is known as Satchev rule, already discussed in chapter 5. 16th, reduction of alkyl halides on treatment with nascent hydrogen produced from a metal and an acid or ordinary hydrogen in the presence of catalyst. Alkyl halides get reduced to form hydrocarbons Rx plus 2H. In presence of ZnHCl, RH gives rise RH plus HX. For example, ethyl bromide plus 2H in presence of zinc or HCl gives rise ethane plus HBr. 17th, reaction with active metals. Alkyl halides react with active metals like lithium, sodium, and magnesium to form different products. A. Reaction with magnesium. Formation of Grignard reagent. Alkyl halides react with magnesium in dry ether to form alkyl magnesium halides known as Grignard reagents. For example, ethyl iodide plus magnesium in presence of dry ether gives ethyl magnesium iodide. Grignard reagents themselves command tremendous synthetic importance. B. Reaction with lithium. Alkyl halides react with lithium in dry ether to form alkyl lithium. For example, N-butyl bromide in presence of dry ether gives N-butyl lithium. C. Reaction with lead sodium alloy. When heated with an alloy of lead and sodium, alkyl halides form tetra-alkyl lead. For example, 4C2H5Br plus 4Na by Pb gives rise tetraethyl lead plus 4NaBr plus 3Pb. 18th, isomerization. On heating to about 573 Kelvin or even lower temperature in the presence of a Lewis acid such as anhydrous AlCl3, alkyl halides undergo isomerization to form products in which the position of halogen is changed but carbon skeleton remains the same. For example, N-butyl bromide in presence of dry ether gives secondary butyl bromide. Types of nucleophilic aliphatic substitution. First order and second order reaction. We have learnt above that alkyl halides undergo a variety of nucleophilic substitution reaction. It is interesting to note, however, that all nucleophilic substitution reacts do not take place by the same mechanism. On the other hand, there are two different mechanisms possible for nucleophilic aliphatic substitution. These are bimolecular nucleophilic substitution or unimolecular nucleophilic substitution. Let us illustrate this mechanism by considering the hydrolysis of an alkyl halide by hydroxyl ion. Bimolecular nucleophilic substitution or SN2 reaction, where S stands for substitution and for nucleophilic and 2 for biomolecular. According to this mechanism, the reaction is believed to take place by a concerted process involving a single step attack of hydroxyl ion or any other nucleophilic reagent take place simultaneously with the loss of halide ion, that is the bond between carbon and hydroxyl ion is being formed at the same time that carbon halogen bond is being broken. OH negative plus Rx gives rise ROH plus X negative. This means that the rate of the reaction should depend on the concentration of both the reagent. As such, the rate of the reaction may be expressed as R is equal to K into concentration of Rx or concentration of OH negative. Since the rate of the formation of alcohol is found to be proportional to the concentration of both alkyl halide and hydroxyl ion, the reaction is said to follow second order kinetics. A single step nucleophilic substitution reaction of this type, which proceeds by simultaneous collisions of two particles, is known as bimolecular nucleophilic substitution or SN2. A simple and prominent example of SN2 substitution is provided by the hydrolysis of methyl bromide by hydroxyl ions in aqueous solution. The reaction may be depicted as It may be noted that the hydroxyl ions attack the carbon on the side opposite to bromine because the attacking nucleophile cannot approach the methyl bromide molecule from any other side due to repulsion by the negatively polarized bromine. This is referred to as backside attack and is supported by stereochemical evidence. As the hydroxyl ion approaches the carbon atom from the backside, a transition state is reached in which there is a partial formation of COH bond and at the same time a partial breaking of CBr bond. The central carbon atom in the transition state acquires sp2 hybridization. As the electrons on hydroxyl ion begin to be shared by carbon, the negative charge on the hydroxyl ion decreases. Similarly, bromine develops a partially negative charge as it partly removes the pair of electrons shared with carbon. The transition state is quickly transformed into the final products, methyl alcohol and bromide ion. Since the formation of transition state involves collision between two particles, the reaction is obviously bimolecular. This is confirmed by the fact that the rate of reaction depends upon the concentration of both the hydroxyl ion and methyl bromide in accordance with rate equation 5.1. The energy profile diagram of reaction is shown is fig 5.1. Stereochemistry of SN2 reaction. The postulation of backside attack by the nucleophilic reagent in SN2 reaction required that the configuration of the product should be opposite to that of the reactant. This has been found to be so in actual practice and can be clearly shown by considering the alkaline hydrolysis of optically active 2-bromo-octane CH3CHBr C6H13. It should be worthwhile to note before proceeding further that 2-bromo-octane has the same configuration as 2-octane as shown below. Now the hydrolysis of 2-bromo-octane with aqueous sodium hydroxide solution follows SN2 mechanism and result in the formation of 2-octanol in view of similar configuration of 2-bromo-octane and 2-octanol. The configuration of 2-octanol must be opposite to that of 2-bromo-octane, as such the reaction may be represented as. It is apparent that the OH group occupies a position opposite to that previously occupied by Br, or in other words, the configuration of alcohol is opposite to that of bromide. Such a reaction in which the configuration of a product is opposite to that of the reactant is said to take place with inversion of configuration. All SN2 reactions proceed with complete inversion of configuration. Note: it is not necessary that inversion of configuration in a reaction must be accompanied by a change in the direction of rotation of the new compound formed and vice versa. This may happen in some cases, as in the example cited above, and may not happen in other cases. It may be recalled that two different compounds which rotate the light in the same direction need not necessarily have the same configuration. Factor influencing the occurrence and rate of SN2 reactions. The occurrence of SN2 reaction and their relative rates in different cases depend upon the following factor. Nature of alkyl group in alkyl halide. Steric factors. In order to compare the relative reactivities of alkyl halides in SN2 reaction, let us first study the effect of size of the groups attached to the carbon carrying the halogen atom. To understand this, it may be noted that in case of the hydrolysis of methyl bromide, the reactant and the product contain tetrahedral carbon, but in the transition state, the carbon is bonded to 5 atoms. When the hydrogen atom is methyl bromide are successively replaced by larger groups such as CH3 and C2H5. There is an increased crowding around the central carbon. This gives rise to particularly strong non-bonding interaction in the transition state because of the presence of 5 groups attached to the same carbon. As a result, the energy content of the transition state rises and so does the E act for its formation naturally. Therefore, the rate of the reaction slows down. It is clear from the above discussion that the relative reactivities of alkyl halides in the SN2 reaction are mainly related to steric factors. In keeping with this observation, the order of relativity reactivity in such reaction is found to be methyl halides, primary halides, secondary halides, tertiary halides. Electronic factors. Let us now have a look at the electron distribution in the transition state and the reactants in SN2 reaction involving hydrolysis. In the transition state, there is partial formation of bond between carbon and hydroxyl ion, which tends to impart a negative charge to carbon. At the same time, there is a partial heterolytic cleavage of carbon halogen bond, which tends to impart a positive charge to carbon. Since these process occurs simultaneously to net charge on the carbon in the transition state is practically the same as that in the reactant. Thus, the stability of the transition state and the corresponding reactant would be affected to the same extent by both electron releasing and electron withdrawing substituents, as much electronic factors have no significant influence on the reactants of alkyl halides in SN2 reaction. Second, nature of halogen atoms in alkyl halide. Elimination of leaving group. In SN2 reaction of alkyl halide, the halogen atom ultimately leaves the transition state in the form of a negative halide ion to form the final product. The more easily the X negative ion is eliminated, the more the rate of the reaction. The ease with which X negative is eliminated depends upon its basicity. The weaker the base, the better it would be as a leaving group. Now, the order of increasing basic strength of halide ions is I negative, Br negative, Cl negative, F negative. Therefore, the order of ease of elimination of leaving groups would be I negative, Br negative, Cl negative, F negative. Hence, the order of reactivity of alkyl halides having different halogens is Ri, Rbr, Rcl, Rf. Nature of nucleophilic reagent. Since the transition state in an SN2 reaction is formed by the attack of the nucleophilic reagent on alkyl halide, stronger the nucleophilic reagent, more rapid would be SN2 reaction. The decreasing order of strength of a few common nucleophilic reagents is Cn, Ro negative, OH negative, CH3CO negative, HO, H2O.